So good afternoon. Thanks everybody for coming to hear about practical steps to achieving asset optimization in 2.5 weeks. So I'm Peter Reynolds. I'm an analyst here with ARC Advisory Group. So I'm going to help facilitate this session and get your wonderful questions over to Mr. Mike Brooks. And I was asked to introduce Mr. Brooks, and most people said, well, he really doesn't need an introduction. But I will say a little bit about Mike because he's going to get up here in a few moments. So Mike's an expert on asset performance management. So Mike was previously president and COO of MTEL. So Mike has 25 years experience with Exxon and Chevron and has done a lot of startups. So without further ado, please welcome Mike Brooks. Thank you.
Thank you, Peter. So, this is the title of the movie. I thought it was 9.5 weeks. So, as Joan Rivers says, can we talk? I want to talk to you today to give you an idea that there is ready-to-use software to do this machine learning stuff very fast, very accurately, with the skill sets and knowledge that you've already got, and scales very rapidly. And I'm going to talk to you about what we can do in 2.5 weeks to prove all that to you. And this is all that blah, blah, blah stuff that says everything I say might be a lie, so don't take any notice of me. So what if? What if you had weeks or months' notice of an asset failure? And it told you exactly what was wrong without having to do those inspections. And not only that, but told you what you could do to understand and avoid the problem, or at least mitigate the circumstances without those false alarms. And it tells you what to do to avoid or mitigate those issues. What if you had a solution that did this? Would that be useful to you? So this is an example of certain seal failures on compressors. And you can see here, a number of them went along here, and you can see the types of things that you get. A warning of 31 days, 31 days, 28 days, 30 days, 30 days. Not unusual at all. Not unusual. What's causing them? To be able to find out those problems is unusual. Here's another one, a recontacting compressor failure. You can see here, 54 days notice. This is your PF curve. We're taking this P point and moving it right out here so you can learn a lot earlier what's going on. Again, 30 days, 49 days. What could you do if you had that knowledge? You'd have time to plan. You'd have time to minimize the impact it's going to have on your lost profitability. Here's another one looking at failures due to liquid carryover. Liquid carryover, the silent killer of compressors. Goes on for months, hardly noticed, and all of a sudden you get the catastrophic failure. What if you knew and understood right the minute it was happening? You could change the operation to avoid it. Not only that, to avoid the maintenance completely. These are some of the things here. You get weeks or months notice. These are real ones. These are failure descriptions. These are the lead times from 5 days, 50 days, 48 days, 56 days. And you know exactly what's wrong. It tells you here precisely what it is with those problems that it's pinpointing. And you'll also notice you don't get the false positives. Now, all this comes from this idea that we've had that we want to improve maintenance. We're not trying to replace your SAP and Maximo system. We're trying to give advice to understand what's going on. Our friends at ARC suggest that 82% of all breakdowns that you are going to have are going to be caused by process-induced failures. And most of the other guys in the business are not even looking for these. Boeing suggests, you know, the guy who's in the cradle of RCM, reliability-centered maintenance, suggests that 85% of all equipment fails on a time-random basis, no matter how much you service and inspect them. You can't find it. One large automation vendor suggests that 63% of all maintenance is unnecessary, and most of it causes more damage than if you left it alone. So the issue is this. The spend is here. All current maintenance techniques are looking for old school wear and tear. That's what they're looking for. So the spend is here, but the problem's here. 82% of your failures here, and we're not even looking for them. So Peter, you can talk about this one. Yes, go ahead, it's yours.
Okay, Mike, I think you're kind of putting me on the spot here, but I'll rise to
I'm sure you can do
the
it.
challenge. So I guess this is something that we would see when we look at the process industries. Oftentimes, operations and maintenance are very segregated. So maintenance tends to focus on a lot of static or rotating assets, and operations tends to focus on a lot of process optimization type activities. So I guess when we study the market, we see that companies are extending the time in weeks and months, and ultimately looking for advanced notification that degradation is going to occur by looking at markers that happen using machine learning and other algorithms, by looking at multivariate data. Would you agree? Or?
Yeah, no, that's fine. I just want to move on from that, because when we draw this curve, we draw it a little bit differently. We've already pointed out that you can get this early warning here. I'm afraid this doesn't work on, there we go. You get this early warning. But if you're looking for those process-induced failures, you can move that P-point even earlier. You can cast a wider net around the equipment, understand what's upstream that's doing the damage to this equipment, sometimes downstream. If you can do that, you can detect that inappropriate operation, and it could be pumps running dry, pumps cavitating, the operator put a wrong set point in, and now I've got liquid carryover. You can find those things. If you can find them, and you can find them early enough, you can stop the damage. This is the holy grail. You can completely avoid the maintenance. We're not talking about reducing maintenance costs now. We're talking about avoiding it and capturing all that deferred product losses. And only AspenTech in this market is stepping up to find out 100% of those issues. The issues when failure is inevitable. The bearings are square. It's going to fail. To give you the time to take action, to plan, to minimize the disruption, and also to find these process failures. So we've done this with what we call an enlightened approach. A lot of the old techniques used to model the machines. Use models, you tune it against the process. If the process moves again, you start getting those false positives. We're not in the business of modeling for this particular application. Trust me, AspenTech is the world's best modeler. If this problem could have been solved with modeling, AspenTech would have done it. But we're in the business of measuring. Measuring the precise patterns of what normal behavior looks like and precise patterns of what failure looks like. Not guessing at them, not estimating them, measuring them precisely. And the assertion that a library of models helps you is false, totally false. You build a model to do this kind of work, you tune it against the process, and then the process moves, it doesn't work anymore, and you start getting those false positives, right? When we set up to do this, we might be looking at a complex compressor with 50 or 100 variables on it. We'll get the work done end to end in an afternoon. With a model, you've got to set it on the plant, you've got to tune it. It takes a lot longer than that. So we've done it with agents. I heard Steve Jobs quoted this morning. But you know what he did for us? He took this piece of equipment here and he said, you know, I'm going to abstract all these complex technologies so that the masses can do it. That's the approach he took. And it wasn't just the screen, you know, using your finger as a pointer. It's all these technologies that do that stuff. We've copied him. We did exactly the same. So we took machine learning, and it's important. We came out of the business. We came out of operations and maintenance. We know and understand this work has got to fit with your work processes and the skill sets you've got. So basically, we encapsulated all the work that you need to do, collect the data, cleanse the data, validate the data, all the alerting, all the focusing. We build what we call these agents that do the work for you. All the monitoring, all that is encapsulated so that a regular engineer, Joe Normal, can do it. That's the difference. So the great thing about having done it this way, this pattern recognition with these agents, they're completely neutral. They only care about patterns. They don't care about what industry you're in. Oil, chemicals, power, they don't care. They don't care what type of asset it is. Mechanical assets, compressors, pumps, but also process assets. We treat them the same way. Heat exchangers, furnaces, incinerators. And also, they don't care which process you're on, whether it's a batch process, a continuous process, reforming, polyethylene, doesn't matter. They only care about those patterns. And the other thing that agents do, see, these agents, they work about every 5 minutes. They don't take bathroom breaks, they don't go home at night, they don't take vacations, and they work forever, learning forever. And one thing that they do is they see things much, much earlier than other technologies. That is, analytics to predict when those maintenance activities are unavoidable. Like I said, the bearings are square. They see things that the others can't. That means looking upstream to see those operations, to be able to change the operations so you prevent the damage. And lastly, our failure agents actually attach directly to the root cause inside the asset management system. So if we give you 40 days notice that the compressor is going to fail, you will know precisely how much it's going to cost, what parts are required, even what lockout, tagout. Everything is known with that notice so you can make the right plans. Agents know how to stop machines breaking. And as we said this morning, we saw some of this. IoT is driving a lot of this activity. And I have news for you. There's a lot of hype around this, and I've heard a lot of it. We've been doing a lot of these things for 35 years, collecting information from equipment and making decisions based on that. What's different about the IoT is only really two things: more and cheaper. That's really, okay, you can get the cloud thing too, but that's just a computer somewhere else. But that's what's driving this, the availability. And because I can do this, I can solve a different set of problems. I can tell you today that what we're doing with the technology, with machine learning, with the capabilities, we are solving problems today that could not be solved 5, 6 years ago. And as you look at this, we're delivering very, very quick results. With an offline trial, we can do this work in about 2.5 weeks. We'll take your data, we'll cleanse the data, we'll link it up to the maintenance data that we also use, and then from that, we'll bring to you a solution. We'll show you it on a system, we'll give you a PowerPoint report out of all that, and we can do all that in the space of about 2.5 weeks. Sometimes less, sometimes more, because we have to do work for other people at the same time as well. So the difference here is that you're going to find the solution is faster, it's far more accurate, very advanced, with the agents doing the work that people can't do. Also very, very scalable. One of the great things about an agent is, if you've got 30 boiler feed water pumps, I don't expect to find all the failures on one pump, or all the anomalies on one pump. But if I've got 30, I can find them, and I can take an agent from one and drop it on the other one, and it works immediately. That means you can scale from 1 pump to 2 pumps to all the pumps on a unit to an enterprise very, very rapidly. And here's a paper. You can download this, written by Robert Golightly, our senior marketing manager, telling you all about what it means to see the future with this type of analytics and this agent methodology. It's not just the algorithms. It's the way this has been put together to work for you. So, at the end of all this, we are creating this world that doesn't break down. I've been to many, many plants. I've worked at plants. Every place I go, they want to buy these 3 zeros. In this order. Actually, from that order, from the right. We don't want to harm people. We don't want the environmental catastrophes. And we want to prevent the breakdowns. And it's not the maintenance costs that causes the trouble. It's the deferred production that we don't get. So here we are. This is the 3 legs of the stool in the terms of way Aspen approaches the world. 35 years ago, we started off with design principles, pushing what's possible with the designs of equipment. We go now to running to the limits of performance, all performance-based things like APC and the other MES products we've got. Today, it's maintain. And as I said, this is not replacing your SAP. This is telling your SAP when the work needs to be done. And the great thing about this, there's these recycle loops all the way through here. When we show you that PF curve, when we understand this, we can feed back into that. We have other products that will help you understand. Maybe if I use a different metallurgy, this pump wouldn't break down so often. There are things in that cycle that we can build in there to make this whole cycle, for the whole life cycle, improve tremendously. So that's all I've got for a formal presentation. I'll answer any questions. If you want more or you'd like to step up for a pilot, we have a table outside where you can sign up or just leave a business card. With that, questions? Peter.
Questions? Maybe just somebody raise their hand, and I know it's hard to maneuver in this very crowded room. We'll just pass the mic.
Howard Evold, ABB. First, I'll say I'll just totally agree with your starting point here on the way people do maintenance and so on. So I wanted to start by asking you, why do you think these practices have evolved and are so difficult to change? Because time-based maintenance has been around for 50 years, despite the fact that the very numbers you said that 85% of maintenance is actually unrelated, or degradation is unrelated to time. It's caused by the process. That's actually been known since, for instance, Nolan and Heap came out with those numbers around 1968.
Good question, and if you're in my longer presentation, I have a slide that addresses that completely. So you're right, 50 years ago, we were basically all in a position. We'd basically run to failure, and then we'd fix it. We started getting smarter, and we started doing time-based maintenance. This is like taking your car for service every 3 months. We got smarter still, and then did usage-based maintenance. I need to take it every 7,500 miles. After that, we said, well, you know, if we instrument these, we can do condition-based monitoring in semi-real time, and that'll tell me something. And then right at the end, after 35 years after it was developed, the latest silver bullet today is this RCM analysis. Now, we could work with that, but the reality is all these different processes lead to the same thing. And that's where the issue is. They lead to better and more complicated ways to work out when I should service and inspect. Whereas what I've told you is that 82% of the problems are caused by process issues, and we're not looking for those. So that's where the spend is. That's not where we're there. But that is changing. These techniques with machine learning and the like are changing that reality.
Mike, I don't know if it's possible that ARC just ask just one question here before we pass this. I'm holding the mic. I guess I can.
This is because I set you up, isn't it?
Okay, is this a tool for operations, for process engineers who do APC, or maintenance, or all above? Who is using it?
So, good question. It's really designed for the reliability engineer, the guy in maintenance. He's going to look at this, he's going to set up. But before we go away from that, to understand this problem and really get this solved, you have to understand this is not a maintenance problem anymore. This is not a problem that maintenance can solve by themselves. Operations must step up to help solve this problem. If they don't, it won't get solved.
Thanks. Steve Zitney, Department of Energy. AspenTech has invested a lot in the modeling part of the business, and you sort of brush that aside, but can you leverage all of that in what you're doing here? Take your first principles, high fidelity, physics-based models to augment these data-driven...
Absolutely. I came from MTEL, so you know where my allegiances are. AspenTech has a 35-year history and model. It's all valuable. It's all valuable, and we are actually doing that. And if I had a longer time, I'd show you where it fits into the process. If you have models and you want to incorporate them, then you can. And we are actually doing that. Some of it we do under the covers. But the main thread here is modeling by itself is not enough, and sometimes machine learning is not enough. You heard this, I don't know if you heard the sessions this morning. Machine learning is not a silver bullet. It's not going to find the problems by itself. It needs context and guidance to burrow into the right problem set, and sometimes the models can help you do that.
You mentioned your constant failures. If a failure in a plant has never happened before, your physics-based models can be used
They can be
to
used.
augment that. You can use your physics-based models to look at failure scenarios that have never occurred and use that information to augment these data-driven...
But I can also add to
maintenance
that.
type models.
We build two types of agents. One's called an anomaly agent. And to get to an anomaly agent, we take all the signals, maybe 50 of them, and condense them down with proprietary technology to what we call a probability waveform. We might be looking at 5 years worth of history, right? And now it tells you the probability of failure at every point in time. In order to make sure that we know if there's a deviation from normal, we take out all the failures we know, we take out all the offline conditions, we take out the hidden failures. That's the spikes that weren't recorded. If we can tag them, we can. If we can't, we strip them. And we're left with a line that's very close to zero. And that's through all seasons, through all operating conditions, startup, shutdown, all campaigns, all batches. And it gives you that line that's very close. That's the purest signal of normal you get. So if we get a deviation from that, we know it's not something that's not right. And frankly, we use machine learning. You know how the credit card does this? Sir, are you in Italy right now? They've learned your normal spending behavior, and then they're looking and they've seen a deviation. We're doing exactly the same with the machines. Okay, we've seen it's deviated from normal. We can put an inspection request directly into SAP or Maximo. You go and take a look, and you come back and check one of two boxes. Yes, it's a failure. Or no, I changed the operation, for example. I put a compressor in recycle mode. If you do that, the system automatically adapts to all changes in process. It will never fall behind. It won't go out of calibration. It won't give you those false alarms. However, if you tell me it's a failure, remember I found this failure doing anomaly detection. That means I asked, was this condition normal? Once I know it's a failure, I ask a different question. I say, what was the exact pattern that led to this? And the answer for that comes earlier with greater accuracy. So it means this is a system that's improving over time.
Tony Howell with General Motors. What are the resources required from this system via the network and computing resources required to implement it?
So we basically built our product on connectivity. So we connect to just about everything. The two places we like to go is to the maintenance system to pull out the work orders, the asset hierarchy, the asset taxonomy, and also to the historian to get the tag dictionary and then the tags. So we can meld all those together to start solving the problem. So it's realistically, this is a system scales very easily from one Windows server to multiples to Linux boxes, Hadoop clusters, you know, from small to complex to simple, local to remote. We scale all the which way. But simply stated, it's a Windows server. We can start off on a small project with that, usually beefy. We like 64 gigabytes of RAM, 128 is better. You know, because the computations are quite intense, but that's what it is. It's not intense in terms of the, you know, what's required to get started.
Other questions?
So a little bit about models. Models are not only the chemical engineering or fundamental models. Anything that mathematically is a model. The machine learning techniques are neural nets, that a model. Support vector machines, this is a model because it's a okay. The fact that you need 2 or 3 weeks of data, that means that you are training a model. Is that correct?
You're absolutely correct.
So
and what I want to tell you, there's a model underneath this. You don't need to go anywhere close to it. You don't have to understand it. That's the difference.
That's why we never understand the neural nets, models, and so on. But you have a model that you need to train. Is that correct? You said yes.
We need to have the data to be able to train to make that model underneath the covers that you don't have to see.
Right. Okay, that's clear.
Yeah.
Now, so how many data you need? If you change...
Say again?
You change the operating conditions. I don't know about compressors very much, but I know about heat exchangers. If I change the bypass of heat exchanger or something else, do I have to do the same exercise?
If you change something and it changes the signal patterns coming from that machine that we're looking at or that piece of operational equipment, it will give you an alert saying there's something deviated from what the system knows is normal. If you know that it's normal, you check the box. Okay. We take that signal, we add it to baseline normal, so you will never get that a false alert from that. It will adopt that as part of its normal modeling. That's how it'll change as your process changes or drifts.
And the same with the instruments. If the instrument gets out of calibration, which is very often, if the valve gets stuck, so you will get all these false alerts, right?
We have proved out that we capture those failures far faster than anything else. We understand when an instrument goes out of bounds. That's not built into the model, that's outside the model. We will tell you. Not only that, we can lose 5% of the sensors coming in and the model will still work and still give you answers.
Michael, nice presentation. Michiel Thijsling from Dow Chemical. Do you have actually practical examples where you made lots of money using this approach?
We have lots and lots of use cases, and it's probably not appropriate for me to go through them all here, but certainly I can spend time with you.
Look, can you mention one that is appealing in the presentation?
Well, I'll tell you a couple. First of all, we did a lot of work with a railway company doing lube oil analysis on the types of engines that use. 4,250 locomotives are now protected by us. We have completely eliminated catastrophic failures on those engines. We've done work on compressors where we found 3 cases of liquid carryover, which have been eliminated. On another compressor, we found in the history was a pattern that led to a 3rd stage valve failure. We built an agent to look for that, and after about 8 weeks, it popped up saying, this failure is coming in 8 weeks. We told the operations sent their guy out, and the maintenance guy, you know, the guy with the fat fingers and gloves on, he leaned against it with his screwdriver. He said, no, it's okay. They left it. 7 weeks later, the state-of-the-art vibration system kicked in, telling you there was an issue. After 3 days, it was so bad, they had to shut it down. When they shut it down, they found exactly what we'd forecast 7 weeks before the state-of-the-art vibration system.
So maybe it's good to have a discussion offline. Thanks.
Okay, great, thank you.
Good afternoon. My name is Simon Scaffetti from Fincantieri. I just want to share some experience that I'm facing with our customer. What happens, for example, if you have like a catastrophic failure? So our customers, they always go back to us and they say, okay, you want to install your system, your telemetry system, but you need to take the warranty of the engine because we pay you guys for avoid catastrophic failure. So if you have a catastrophic failure, what happens? Because the customer is paying to avoid catastrophic failure.
So there's a couple of nuances on this. There are systems that are made to shut down to avoid catastrophic failure. There's things like compressor controls does. If you go into surge, they'll shut down. That's not the system we are. We are looking for that degradation that starts and builds up over weeks and months and then leads to the failure. So we're going to be able to tell you well before that happens. I'm not going to tell you if the main shaft snaps. I don't know anybody who can tell you that actually, you know, but that's not what we're after. We're after that degradation that happens and carries on over time, over a long time. And we see this in pumps. We've been able to give 4 months notice that pumps are going to fail, you know, electrical motors, turbines, compressors. And we've even done static equipment, heat exchangers, incinerators, boilers. We've been able to do that kind of equipment as well. Because the patterns don't lie. They don't care. And we're measuring the patterns, you know, to tell us what's normal and what's not normal.
Mike, I just got another question. Now, the CSX story, I remember they presented here 2 years ago, so we had an opportunity to meet with them. But what I don't remember is there's this idea of employee change management and all the work that's involved in changing your organization to stop doing things that are not value added versus there's just plain training on using the tool. What's your experience on both of those topics?
So I think that's a really good question, you know, and we kind of came into this. I told you, we came out of maintenance. We came out of operations. We've seen this stuff. We stepped out of the box, say, how can we make a difference on this? We took a different approach to do it, you know. But when we did this, I remember some advice I got from a large oil company many years ago that basically said, you can bring us the technology, but if the technology forces into new work processes that we're not familiar with or hard to do, the technology is no good to us. So when we started off, we had a laser focus to make sure this works with the work processes already in place, with the skill sets of users already there. So they didn't have the burden of having to change those work processes and learn new ones. That's what we did.
Other questions?
Hey, Mike. Gary Lipson from Ashland. 2 questions related. One, can you speak to, beyond obvious benefits on a continuous process, how this would work with batch? And also, when you talk about getting the data that it's looking at, pulling it from historians, Aspen, as well as many of the other historians, will do data compression and whatnot. Can you talk to the fidelity that you need of the raw data coming in?
So what was the first one again?
On batch.
Batches, yeah. So we've done quite a bit of work on batches. You know, we started off looking for things that fail. But a number of customers have asked the inverse question. What can you tell me? Why can you tell me some things are better, good? You know? So we looked at drilling optimization. Tell us which are good ones. We looked at batches. Which are the good batches and why? And if they drift early on, can I catch that drift with an anomaly and then correct it? So we've done that. We did limited work in semiconductors doing the same kinds of things. Now, in terms of the historian, yeah, we connect to everything. I mean, we start off our business doing connectivity, especially to historians and to, you know, to maintenance systems. In terms of when we do this work, this will surprise you. We start off with looking at samples of data once an hour. So the compression doesn't become a big issue in that at all. We usually end up, well, that gives us an idea of the scope of the model, what we need to do, and we usually come down to where we run every 15 minutes or every 5 minutes. Now the truth of it is, if you have non-compressed data, that's better, but it doesn't mean to say you can't solve it if the data are compressed. That's been our and we've even gone down to millisecond data for some certain types of problems.
Any other questions? Havard.
Maybe I should take this offline, but it's really interesting to discuss. It's about data and measurements. I mean, what you don't measure, then you can't know
Correct.
about it, right?
First thing you have to have is data.
So do you have any mechanism that will tell you if your data set is in fact deterministic?
Yes.
Or, I mean, you mentioned the 5% loss of sensors, and that would obviously mean that your system is over-deterministic in some way. And you would need to know exactly for the pump or for the compressor and so on, do I actually have the data I need in the system? And that's actually often a tricky process to verify. And of course you can substitute data because you got head pressure from some other device and something, but some comments around that.
So yeah, like I said to you, when we start off this runs the same ilk as what we used to call in the past, you know, business intelligence. You know, and if you understand when we used to do that, there's all this work to bring in the data, validate the cleansing. We used to say it's between 50 and 80% of the work. We recognize that. So we put a number of tools at the beginning to automate this work, looking for 8 different quality characteristics. We'll be the first ones to tell you that your DCS is wired the wrong way. To the historian, the tags are mismatched. We'll do those kinds of things. We'll tell you that all your data is not complete. You've got some flat lines here. You've got some that's extremely out of bounds. You know, so we do all that work automatically. We set this up so it automate that process. So that's that part of it. I forget, what was the rest of it? Does that answer it?
That was more, do I have the data?
Oh, okay. So he's... Well, I address failing sensors, but if you lose data, you lose communication, usually what happens, we'll catch up later, and then we'll scan it then. So, I mean, and this is not us, if the failure is going to happen in the hour when you're not collecting data, then we wouldn't catch it, but that's very unlikely for the type of work that we're doing. But what I will tell you is that we did work for one metals refiner with large slurry pumps. They only had 4 sensors on them. Pressure in, pressure out, fluid temperature, and motor amps. As a result of the patterns we found, we gave them 2 weeks' notice the motor was going to burn up. And of course, the first message, they ignored it. You know what happened 2 weeks later? The motor burned out. Since then, it's been a total change in maintenance culture. Their RCM team is now a SWAT team, understanding how to respond when we give them that alert, that heads up. So that's with 4. Now, on some very large pumps in refineries where there were 50 tags, we'll give them 4 months and 5 months. So the difference is the number of sensors that you've got and the quality of the sensors will tell you earlier and more accurately. We usually recommend at least 5. For a compressor, I'd say more. But usually compressors are well instrumented, so we don't have the big issue there. No, it's more complicated than that. It's one data set for one piece of equipment, which can be divided into subsets to look for different problems. You need the training class if we need to go further. No worries.
Yeah. Mike, this is one question that I know ARC gets often is we find that most companies are piloting machine learning and analytics across batch or continuous process. But companies also want to know how to scale up quickly and move this across 50 plants, 100 plants, global locations. Do you have any recommendations on how to quickly scale up something like this?
Yeah, I mean, if we're going to do a whole enterprise, what we like to do is start off with one unit at one site, get that running, get the staff trained up so they can take it forward by themselves. This is easy to do. They always learn to do that. And then move to another plant and repeat that. The other thing, as I said earlier, because our agents are scalable, because we can learn on one piece of equipment, transfer, that makes it very rapid to scale through an organization. That keeps us safe. If you've got a pipeline, they've got the same 4 compressors at every station for 300 miles. So we can learn on one set and transfer it to the rest. And like I said, we did that with those locomotives. We started off with the 18 bad actors, learned the patterns, transferred them to 600 for a trial, and in 4.5 months, saved 6 locomotives. That was worth $10 million to that company. You wrote about it, so you know. So that's the kind of things we've been able to do. Yeah.
Questions? Yes.
Apostolos Giorgio from ExxonMobil. Is that the alerts you send, are they to the operator or to the engineer? What is, I didn't understand that.
The what, sorry?
The alerts, when you say...
the alerts go to, really the alerts can go to any subscription list, anybody you want. But primarily they're going to go to the operator because he's going to get an alert and he wants to say, okay, I got an alert. It's going to fail in 40 days. What do I do?
Right.
So he needs to know.
So
the reliability engineer or the maintenance guy, he needs to know because he has to respond.
Okay, the first alert goes to operator. Let's agree on that. Do you have data to give us the false positives for the operator? Any data from previous cases you have?
We've got very, very few false positives. We're in the very high 90s in terms of the accuracy of our results. Very, very few. And it's because this agility that we have to change with the process, change it, as you said, change the underlying model automatically with very simple processes. So very, very slight. 99% and above, yes. That's not the false positives, that's the opposite.
Questions? 20 minutes left?
We got 20 minutes?
Yeah.
Come on, guys.
We finish up at the top of the hour, is that right, Mike?
I thought it was 45 minutes.
Oh, 7 minutes, okay. I stand corrected.
So the question I have is, you talked about identifying one equipment, but in a given process, you might have 100 devices. So are you going to work on the whole process or just one piece at a time? The reason I'm asking is, you talked about seal failure, you talked about compressor, valve. So you might have 100 devices, and I'm thinking about return on investment. Any one device can cause things to fail. So how your model works?
So basically, if I've got one piece of equipment, I'll basically set up, I'll take all the history you've got, maybe 5 years, one button click. It will do all the analysis, pull in the work orders, it will figure out where the failures are, it'll tell us where the hidden failures were, it will tell us what normal looks like, so we'll build an anomaly agent and all the failure agents. That'll get done for one compressor in an afternoon. At the end of that, you can do all those tweaky things that data scientists like to do without knowing. You press a couple of buttons and it'll go, and it might spend 4 hours churning to do all these things, and it'll come back with the 3 best agents for any one particular failure. And you can see them in terms of time to failure and accuracy and pick the right one. Now, if you've got 3 compressors at the same, we'll do those together. So it's the same work, same process. So that's how it scales very rapidly. But you're right. What usually happens is the customers, a lot of our customers do all the work themselves. All they need is a little leeway, a little training to get started. So we might help them with 25 or 50 assets. Then after that, they'll take it and run it with it themselves.
Questions? Okay, there's got to be some more questions here to make Mr. Brooks sweat.
Steve Zitney, Department of Energy. How do you determine the initial state of the asset or plant? Because you might have an existing level of degradation for different assets, so when you're establishing your baseline.
Yeah, so there's two ways that we do that. One is, it's greenfield, we've never seen it before, you have no history, then you have to start. You'll run for a couple of months and we'll learn what normal looks like. Thereafter, hopefully you don't get any fails in the first 2 months, but thereafter we know what normal looks like, and then we'll start giving you alerts based on anomalies, and we'll correct those into failure alerts where they're failures. So we'll do that. If, however, you've got 5 years of the history, we'll go and we'll look at the patterns through there. So, and I remember one time we went to a refinery, we found a pattern that led to a drive coupling failure on a pump. Another one that led to a seal failure, bearing failure, and basically we built 2 agents for that, plus the anomaly. So on day 1, you got 3 agents looking after it. And then there's a number of other pumps that were the same. We found different failures on those and put them. So you start off on day 1 with 4 or 5 agents that are all going to protect that piece of equipment.
Is this whole process, like from a UI perspective, dependent upon, proprietary AspenTech dashboard alerting this, or can it be integrated with an already existing, data lake process, dashboard that's built, that kind of thing?
Absolutely. We made this completely universal in terms of where it can get the data from, where it can send the data from. And we work really hard to make sure that you don't have to be a data science to do it. But if you really want to be a data science, we have an API. So we'll do all the grudge things, collecting the data, massaging it, putting it into the right groups, and then we can send it through an API so you can use Google TensorFlow, Microsoft Azure, SAP HANA, any one of those general platforms, Azure, to do those things. So we give you that, and also that scalability.
Got a question over here. You might have touched on this a little bit on the previous question, but on a new failure, how will the system know that that's a failure? Would require interaction from an end user, or would you go back to SAP and pick up a related work order? How would it know it's a new failure?
If it's a new failure, we don't have it recorded. We don't know that pattern. We don't have a link into SAP. It'll come up, it'll give you an anomaly alert. We will send a work order into SAP asking for an inspection. You go out and take a look and you check 1 or 2 boxes, failure or normal. If you select failure, now it's incumbent on you to do the RCA analysis to figure out what the root cause is. If you put that into the SAP system, then that new failure will link to that. So next time it happens, we'll tell you exactly what it is.
So in the absence of connectivity to SAP,
yes,
you will require somebody to go in.
When we do this, it's like going to the doctor. When you go to the doctor, right, he doesn't just use the stethoscope, right? He uses the patient history. It looks in there to see what happened in the past. How were you treated? How did you respond? We're doing exactly the same with the machines. You can't solve this just with the sensors. You have to have other information sources. Maybe it's a downtime tracking system, because you want to do what in machine learning is called supervised learning. I know what the event is, and I want to understand the pattern that led to it. So that means that we use those other sources. If we're not doing that, we're only doing anomaly detection.
Understood.
Right.
In the case where you have a train of compressors, they're close to identical, to the extent that they could be identical, and you have seen a certain type of anomaly or failure in only one of them, are you able to train the model, tell the model that what an anomaly in another compressor might look like based on what you know from the one compressor?
Yes, we've just had a very successful one with an oil company on some very large compressors where they were getting failures costing multi-millions of dollars. And they tried all kinds of ways before us, all the other products. We went there and told them what it was. Not only that, we took that from that compressor and then put it on the other 2 trains, and it worked perfectly.
Okay, I think we're 15 minutes before the hour. So, Mike, any parting comments, or will you be around after?
I'll be around to talk to anybody who wants to catch me. And as I said, there's a desk outside where you can sign up if you're interested in a pilot or just want to talk some more. Thank you very much for your time. I appreciate it.
Thank you, Mike.